Okay, so now we are going to talk about noise. So when we're talking about noise, we can make a simple model here for noise in the time domain, like noise as a function of time. So this typically happens if you have a telescope that's trying to measure something, and then it gets data as a function of time. And that's often the situation we are in. So here we're talking about white noise. That's the simplest kind of noise, and that's the kind of noise that we like. So in that case, so we have this simple model. We have the data, and the signal, and the noise. And the noise here is just given by some Gaussian that's independent at each time step. So we just have lots of independent random samples from this Gaussian distribution with the variance sigma naught squared. And that's equivalent to this noise covariance matrix, which is just a constant. And when we have noise like this, then we see that it doesn't bias our signal in some way. And if we have enough signal to noise here, like we have here, then we can clearly see the structure of the signal. And if we want to measure the signal, then in general, when we have white noise, the error bar or the variance of our signal estimate will go down like 1 over the number of samples when we add more data, add more samples. So this is like the ideal. It's not possible to iterate down better than this. Okay, so the more complicated case, but also the case that we usually see, is when the noise isn't completely uncorrelated, but we have some correlations in time. And we see here that noise like has some large scale structure here. We still see these short time scale noise, white noise fluctuations, but we also see these longer time scale random fluctuations here. So the data is correlated with itself in time, and that makes things much harder. So if you see here, when we compare, we look at our actual data, we see that it still sort of follows the signal to a certain extent, but there are also lots of structure here that's not coming from the signal, and that's coming from the correlated noise. And it's hard, like if we didn't know what the signal was here, it's very hard to distinguish what is actually signal, what is actually noise. And that's why you need like more advanced map making techniques and stuff like that in order to take this uncertainty into account properly and get the best possible estimate of the signal. Okay, but so in this case we have some we don't have white noise, but we have these correlations. But what is actually this correlation matrix? Well, we have a nice simple model for that works in that is good approximation in many cases, and that is called 1 over F noise. So so the idea is that we have a noise covariance matrix like this, which is diagonal in Fourier space. So it's given by multiplied by the sigma naught squared, and then we have this first term here. This is just the same term as we had for the white noise, but then we have this second term as well here with the frequency, the temporal frequency, and a parameter here called the knee frequency, and a parameter here called alpha. And this alpha is typically a negative parameter. So this means that we have f to some negative power, and in some cases a can be close to 1, and that's like we call it 1 over F noise, but it's usually 1 over F to some power, and that power is alpha. And if you look at this power spectrum in Fourier space, it looks something like that. So the data will be this blue here, and that will be flat here. So here it will be dominated by the white noise part, and then this first term here, and then at low frequencies, this correlated term will dominate. So low frequencies corresponds to long time scales. So on long time scales, the correlated noise dominates. On the short time scales, the white noise dominates, and that makes sense from what we saw in the previous slide. But of course, we can change if we change the parameters here, we change where this correlated noise kicks in and what kinds of timescales we get correlated noise from. So here we see 3 different cases. So we have a knee frequency of 0.5 hertz. Then we get slowly moving. There's still correlations here in the green one, but it's slowly moving. Then we have the red one here with a knee frequency of 1 hertz. Then it's moving faster, not that fast, but there are correlations on shorter timescales here. And then we have knee frequency of 2. There we see more structure, more correlations on shorter timescales here. So generally, we want to have a knee frequency as low as possible, and instrumentalists use a lot of tricks in order to get the knee frequency down to as low frequency as possible, because then it's much easier to distinguish the correlated noise from the signal, because what we actually want is to have the knee frequency be lower than the time scales where we actually measure the majority of the signal. And in that case, we can disentangle the fluctuations in the data coming from the signal and the ones coming from the correlated noise. But that's not always possible, and then we need to take it into account through map making and stuff like that. Okay, that was a short introduction to noise and correlated noise. Thank you.